All right, today we are going to be doing section 4B.11, which is our chapter 10 first set of notes, creating equations. So by the end of this video, you should be able to create an equation given context, graphs, coordinates. All right, so the four main types of equations that we're going to focus on for today are exponential equations, linear equations, so a little bit of math 1, quadratic functions, so a little bit of math 2, and then logarithmic functions, a little bit of math 3. Types of variables. Independent variable is labeled on the x-axis. The quantity that changes based on values chosen. That's why it's the independent variable, because we get to pick whatever value we want for x. It's also called the input because you will input that value in to then get your dependent variable, which is labeled on the y-axis, and that's the quantity that changes based on the input values of the independent variable, also called the output variable of an equation or function. So let's take a look at our first example. An aquarium supply manufacturer conducts yearly follow-up customer surveys in order to track the performance of its products. The graph shows the percentage of aquarium heating elements that customers reported had to be replaced over the course of 7 years. Identify the independent variable. So in this case, our independent variables, time in years, it's also labeled on the graph, but from context, you can tell too. Identify the dependent variable. Our dependent variable in this case is percentage of replacements. Again, it's labeled on the graph, but you can tell from the context as well. How does the independent variable relate to the dependent variable? So looking at this graph, it appears that as time increases, the percentage of replacements decrease. And what type of equation, exponential, linear, quadratic, or logarithmic, would this graph represent? Explain each in terms of the graph relationship between the time and percentage of the replacements. So again, looking at this graph, it appears that it's exponential decay, but it could potentially be quadratic if it was to eventually come back up. And it could also potentially be logarithmic with a reflection on the x over the x-axis. So all three are potential graphs or models. What are some of the limitations of the values and percentages and time variables in this example? Well, that's asking about the context. What are some restrictions we have based on the context? So in this case, our domain or time in years has to go from 0 to infinity, and our range would have to go from, based on, again, the graph, 6 to infinity. All right. Example number 2. Aaron wants to have his company's logo printed on tablet computer cases so that he can give away the cases as part of a marketing campaign. A specialty printing company will charge Aaron $750 fee to design and print the personalized cases plus the cost of the actual cases. The price of each case is $3. How many personalized cases can Aaron purchase if his budget is $1,200? So write an equation for the cost of n cases. So in this case, since it's a flat fee that we're paying, and then there's a constant increase per case, it'll be a linear model. So writing our equation, we can have T equals 3n plus 750, where again, n represents cases, T then would represent total cost. Determine the number of cases Aaron can buy. So we go ahead and we substitute in 1,200 for T, solve for n, subtract the 750, then divide by 3, and we get 150 cases. Example number 3, Chloe is driving back home from college for summer vacation. She fuels up her gas tank and then drives for a certain amount of time before passing the world's largest ball of twine. She drives on without stopping, and 3 hours after leaving her college, she has driven 120 miles past the world's largest ball of twine. 7 hours after leaving her college, she has driven 400 miles past the world's largest ball of twine. Assume Chloe is traveling at a constant speed without stopping. So again, constant means that this is going to be a linear model. I need to kind of graphically visualize this. So I'm going to start there, plotting where she is with respect to time, distance with respect to time, and really distance and time with respect to the ball of twine. So find Chloe's speed. So using the fact that we went 280 miles in 4 hours, we can get that she has traveled 70 miles per hour. How far has she traveled before passing the world's largest ball of twine? So X is what I'm looking for here. So I know that it took me 3 hours to travel from home to the ball and then 120 miles past that. So X plus 120 divided by 3 equals 70, right? Because miles over time is miles per hour, miles over hour, to get the speed. And then we can multiply by 3 and then subtract the 120 and get 90 miles. Write a linear equation of one variable for the distance Chloe covers in t hours. So again, using that formula, distance equals rate times time, or a linear model with no y-intercept. We have distance equals 70t, or d equals 70t. And then find the domain and range of the linear equation. So our domain in this case is 0 to infinity, and our range would then be 0 to infinity, assuming that she doesn't stop there, keeps going. All right, example number 4. Write a quadratic equation in one variable that is true to the 3 data points by solving a system of 3 equations based on the standard form of a quadratic equation. Then use your equation to find the y value for a 4th point on the same graph that has an x value of -4. So in Math 2, you learned a few ways to do a problem like this. I'm going to expect you to solve it algebraically or with matrices, not with a linear regression. So let's start first by creating our equation. I know x and y, and I know 3 different pairs of x and y, so I can get 3 different equations, which we need because we're looking for 3 variables, a, b, and c. So if we're looking for 3 variables, we need 3 equations. So we substitute in the coordinates. 1, 5, 3, 21, and -2, 26 to get our 3 equations. So we have 3 equations in 3 variables. So again, you can solve this algebraically with the matrices or with a regression. I'm not going to allow you to do it with regression. I want you to do it algebraically or with matrices. I'm going to use matrix because it's a lot easier. So we set up our matrix. We have our coefficient matrix 1, 1, 1, 9, 3, 1, 4, -2, 1, which again come from our 3 equations, the coefficients of A, B, C. And then we have ABC, our variable matrix, equals our constant matrix, 5, 21, 26. And if you were to multiply this back out, you would get the original equations. Because remember, matrix multiplication is row times column equals the element in that row in that column. So we'd have 1a plus 1b plus 1c equals 5. And then et cetera, et cetera. We'd have 9a plus 3b plus 1c equals 21. And then 4a plus -2b plus 1c equals 26. And that's how, again, you do matrix multiplication in case it's been a while since you've done it in Math 2. All right, so Entering this into our calculator, we enter that first matrix in for A, and we enter that matrix in for B. So if you forgot where matrix is in your calculator, looking at your calculator, we have matrix is right here below math. So we'll hit second inverse to get to our matrix. And then we're going to scroll over to edit. We scroll over to edit and then we hit enter. And then matrix A is going to be a 3 by 3. And then you enter in matrix A. So 1, 1, 1, 9, 3, 1, 4, negative 2, 1. So now I have matrix A entered into A. And then we go back to our matrix menu. So second inverse again to get back to the matrix menu. And then back to edit. And now we're going to go down to B. And we're going to enter in matrix B, which is a 3 by 1. 3 by 1. And we enter in matrix B, which is 5, 21, 26. So now I have that. And then you completely quit. So you have to go to the home screen and then you go back to your matrix. So again, second inverse. And then we're going to enter in matrix A. So we're not going to go over to edit this same time. We're just going to select matrix A. And then we're going to hit the inverse button. And then we're going to go back into our matrix, select matrix B. So we have A inverse B, and then we hit enter. So A inverse B, and we end up getting 3, negative 4, 6. So that means A is 3, B is negative 4, and C is 6. So that means our equation of our quadratic is y equals 3x squared minus 4x plus 6. So now we can answer this last part. Find the y value of a fourth point on the same graph that has an x value of negative 4. Substitute that into our equation, and we end up getting that coordinate to be negative 4, 70. Example number 4. The data shows the current in milliamps in a cell phone circuit in fractions of a second after a cell tower signal is received. So we have time in t, time in seconds, and current in milliamps. Graph these points on a graphing calculator. Use the graph to write an exponential equation of the general form y equals a times b to the x that approximately fits the data. So in this example here, we are going to want to do a regression. So to do that, we hit stat and then edit. And then in L1, we put our data for time. In L2, we put our data for the current. If for some reason your L1 and L2 are not there, when you first hit stat, the fourth option, which says setup editor, you'll have to run that setup editor, and then your L1 should be back. Occasionally your L1 disappears. All right, so now that we have our data in, we're going to go back to stat, scroll over to calculate, and then in this case, I lied. First, we want to look at the scatter plot because we want to see what it looks like. So we're going to go to our stat plot, which is second y equals, and then make sure that your stat plot is on. turn that on, and make sure that it's on scatter plot, because remember we did do some histograms last chapter, so just make sure it's on a scatter plot, and then hit zoom 9, which is zoom trig, and then we take a look. So looking at this data, it looks exponential. So I think calculating an exponential regression would probably be best. If for some reason it's not, your calculator may give you an error, and then that means we might want to do a natural log regression or potentially a quadratic regression. So, oh, the example did say use a graph to write an exponential equation. So we do want exponential. So go into stat again, over to calculate. So stat, calculate, and then exponential regression, which for me is option 0, but it might be different on your calculator. And then we should end up getting the following equation. If you're looking at this and thinking, what the heck did we do from here to here? I just cleaned it up a little bit. Noticing that they're both 1.19119. I took both and I just rounded it to 1.2 and 120. All right, then rewrite the resulting equation so that it includes the power of 10. So right now this is 120 to the x power. We need to rewrite this as 10 to the x power. So I can rewrite 10 or 120 as 1.2 times 10 squared. And then using our properties of exponents, multiplication, you can separate. And so then we end up getting 1.2 to the first times 1.2 to the x, which ends up being 1.2 to the x plus 1, because again, multiplying the same base, you add. And then power to a power, you multiply, so times 10 to the 2x. That's just a little bit of math manipulation using our properties of exponents. All right, example number 5. Write an equation in one variable that fits the data points 1, 6, 3, 24 exactly without using a calculator. So since I'm only given 2 points, this could technically be any type of equation. So let's start by writing a linear equation. So y equals mx plus b. So I start by substituting in, or I'm sorry, finding my slope using our slope formula. And then once I know my slope, I take my point, substitute it in, and my slope substituted in so I can find my y-intercept. And now that I have my slope and my y-intercept, I have my equation of my line. Exponential equation, that's y equals a times b to the x. We're going to have to, in this case, substitute both points in. So x and y to get 2 different equations, because I have 2 variables, a and b, that I don't know. And I don't have a formula like slope formula where I can find it. So I have to create a system of equations. So we substitute in our 2 coordinates to get our 2 equations. And now I'm going to actually divide these, because it works out nicely to divide. Since they're both a, we can cancel the a's that way. There's a bunch of ways you could do it. You could have solved for a, substituted in, etc. I chose to divide. So I take 24 equals a times b to the third, divided by 6 equals a times b. So 24 divided by 6 gives us 4. B cubed divided by b is b squared, which means b is both plus or minus 2. So we get 6 equals 2b, so b is equal to 3. The reason why it's the positive one and not the negative one is because this is exponential growth. All right, that is it for our lesson today. Make sure that you're keeping track of any questions you have, and I will see you all at office hours on Tuesday at 4:30 to go over any questions over today's lesson. So I hope you all had a great weekend. I hope you found this lesson informative and you are able to get your homework done pretty successfully. Remember, when you're finished with your homework, to complete that Google form because it kind of is the thing that gives you your credit for doing the work today. All right, stay safe, stay healthy, and please, please, please stay distant. Bye.